Whoa, okay. Okay, so I am learning computer science slash data structures and algorithms the right way, I hope. And this is day two. This is actually day two. Yesterday, but I'm gonna title it day one. Yesterday, this is what I did. Yesterday was the first day, and I learned about what big O notation is, what time complexity is versus space complexity, and trying to find out what the most important algorithms are. And I'm trying to practice each one of them. So I've already done these three, which were very easy, and I've done them in TypeScript right here. So this is binary search, and this is linear search, which is just looping through each element in the array. And then there's bubble sort. So these three were super, super easy. They didn't really need much. Like I just did them from memory based on like I saw them once and then I could just do them. So yeah, today I'm going to continue looking at the rest of the algorithms, the most important ones. And I have this roadmap here, which I am going to trust. It's this one. And the common algorithms are right here. So you have sorting, recursion, searching. I've already done these two. I've done bubble sort, um, graphs and trees and recursions and greedy algorithms. And so I'm going to keep doing these and I'm going to keep looking up videos. So I'm going to do insertion sort right now. And then I'm going to practice it in JavaScript and just see if I can do it and how easy it is or how hard it is after I understand it. So I'm going to go with insertion sort right now.
Welcome back everyone. In this video, let's take a look at the second sorting algorithm, which is insertion sort. The
Now,
problem
sorting
statement
algorithms are
remains the
usually
same.
built in anyway.
Given an array of integers, sort the array. Sorting can either be ascending or descending. For example, if we have an array of 5 integers, passing the array into insertion sort function should
Sure.
return the same array in ascending order. Let's first understand the idea behind insertion sort. With insertion sort, you virtually split the array into a sorted and an unsorted part. Since one item by definition is always sorted, we assume that the first element is
Oh,
sorted
I've watched this
and the
video
remaining elements
yesterday,
are unsorted.
but it seemed
You
hard
then
to
select an
execute,
unsorted element and compare with all the elements in
or
the
harder
sorted
than the
part.
other ones so
If the
far.
elements in the sorted part is smaller than the selected element, proceed to the next element in the unsorted part. Else, shift larger elements in the sorted part towards the right. You then insert the selected element at the
Yeah.
right index, ensuring the sorted part remains that way. Finally, 8, minus 2, and 4. I've omitted the comma as it gets a bit too crowded. Here is how insertion sort works. You begin by assuming the first element in the array is already sorted. Remaining 4 elements are unsorted. You start at index 1, which is the first unsorted element. Let's store it in a variable called number to insert, or NTI for short. You compare it with the sorted elements on its left to see if it is out of order. We have one sorted element, which is minus 6. Let's represent that as SE, sorted element for short. We check if the sorted element is greater than the number to insert. Is minus 6 greater than 20? The answer is no. In that case, place 20 to the right of minus 6. Of course, there is no change in sorted elements.
I've already seen this example,
The next
and I'm
sorted
just
element
thinking
is
how I
minus
can do
6.
this in code.
Is minus 2. So shift to the right. Next is 8 greater than minus 2. Yes, so shift to the right. Next is minus 6 greater than minus 2. No, so place minus
8. It's turned into 20, but the 8 is stored in this variable. And then it just keeps going over. And then if 8 is less than 20, then it's going to replace this. And then now we have the new array, which is sorted. Then the next element is negative 2. And since it is less than 20, it's going to turn into a 20. And then we're going to compare it with this one. Now we're going to compare it with this one now. So since this is less than 8, it's going to turn into an 8 when it's here. and then I'm going to compare to the -6, and it is more than -6, so this is going to turn into -2.
Our sorted part is now
Yeah.
-6, -2, 8, and 20. Finally, the unsorted element is 4. Compare again with the sorted part which lies to the left. Is 20 greater than 4? Yes, so shift 20 to the right. Next is 8 greater than 4. Yes, so shift to the right. Next is -2 greater than 4. No, so place 4 to the right of -2.
So I'm going to put this on my other screen, and I'm just going to try and do it right away. All right, so const insertion sort equal an array of numbers, and that's it. And it's just going to return the array sorted. So we're splitting the array into two parts, one sorted array, which is just the leftmost element, the first index, and then the rest of the array. So does that mean literally split it? Trying to think what the most efficient way is to do this. So if I just say sorted array equals a 0, and then just spread it like that. But I don't need to spread it because it's just one element anyway. So now it's one element in an array. Const unsorted, and then we get the unsorted array equals, and then a dot, what was it, slice? Yeah. And then you can just do slice 1. And that will just take from the second element onwards. And now we can just loop over each element in the unsorted array for let I equal 0, I less than unsorted array dot length -1, I plus plus. I'm going to name this input array for clarity. For each element, we have to store the number to insert in a variable. Let nti equal unsorted array I, and then the element we are comparing it to should be let we had it as SE. I forgot what that stands for, but we'll just say SE equals sorted array dot length -1, which just means the rightmost element. And then it's like if, because we're trying to sort it, so if NTI is less than SE, it needs to go to the left of it in the array, because we're going ascending order. So if NTI less than SE, NTI less than SE. I haven't even seen a solution for this, and I'm just doing it just based off understanding. If NTI is less than SE, then just sorted array dot push NTI, not NTI, SE. And then it needs to check if it's less than the next number as well. Until it finds the number which it is less than. Else if, or just else, sorted array is this a loop within a loop? Because we're looping through each element in the unsorted array, and then we're comparing it to each element in the sorted array. So this should be a loop within a loop, right? And okay. So now we are looping through each element in the unsorted array, and we're storing the variables NTI and SE. But should we first be looping? No, but maybe we should start the second loop here, actually, because the NTI should only change. Yeah. Only change based on the elements we're trying to insert. So for let x equals 0, x less than not unsorted array, sorted array dot length minus 1, x plus plus, and then like this. But we're comparing from the right side to the left side. So this will loop throughout the elements in the sorted array, but it's going to loop from beginning to end. So we could just flip this, right? And use x here instead. And flip this for loop here. Sorted array dot length minus 1. X greater than 0, and then x minus minus. This is easier to understand, I think. And then sorted element, I think that's what SE stood for, sorted element equals sorted array x, which is going to be the rightmost element at the beginning, and then it's going to go move to the left towards the beginning of the array. It's going to start from the end and go towards the beginning. And then if NTI is less than SE, so we need to shift, then we're going to just add SE to the end. And then it's just going to loop again. Else sorted array x equal NTI. That makes sense, right? That makes sense, I think. Because we're looping through the sorted array backwards. And then if the number to insert is less than SE, then we're pushing SE to the end, which means we're adding a new element. And let's say that's the case, it's going to loop again through the, and it's going to go to the next number to the left in the sorted array, and it's going to do that comparison again. And then if NTI is less than SE, And it's going to redefine what SE is, by the way. It's going to be the element that we are on right now. It's going to be the element with the index X. And then it's going to do that same comparison again. And now it's going to shift that number unless it's not less than SE, then it's just going to set that. It's going to set it to NTI. So let me just play it out in my mind to see if it's not going to cause any issues. Or you know what? I'm just going to try it. So console log insertion sort. I hope I got the for loops right, but okay. Let's try it. And we need to return, obviously. Return sorted array. Because it's only being changed through us pushing to it, right? So return sorted array and 2. How did we get 2? Oh no. Two. How did we get 2? All right. X. X. If NTI. What am I doing wrong? How do we get 2? Should this be X plus 1? Maybe? Because it's actually supposed to be put to the right of the element, not on the element. No, didn't do anything. Oh, this should be looping through input array, not unsorted array. Right? No. No, it is supposed to be. No. That's fine. Let's get a console log. There should be no issue here. Okay, so the unsorted array is fine. And just gonna console log loop and then just I. I'm sure it's looping and everything. It's looping 3 times. What about here? sorted array dot length minus 1. Sorted array dot length is 1 minus 1, so that's just going to be 0. So it's not even looping. So, or maybe just make greater than or equal 0. Yeah. Yeah, there you go. Whoa, 17. And maybe this should just be x. Whoa, hold on. So it just wasn't looping, but then there's another issue. What's wrong? 17, 17, 17, 17, 17. I think this is supposed to be x plus 1. 2, 5, 17, 17, 17. Why? Why is that happening? I just want to see how the array is being changed. So I'm just going to console.log sorted array every loop. to 17. Number 2 insert is less than SE. The SE needs to be updated. Yeah. It is being updated. It is being updated. This is getting very hard to visualize for me. Let's just try with positive numbers. Just 3, 2, 1. 3, 3. How did you get 3, 3? I'm a bit lost. So let's, okay, 3, 2, 1 is going in here. Sorted array is going to be 3, just 3 in an array. Unsorted array is going to be 2, 1 in an array. For each element in the 2 and 1, yeah, the number to insert is going to be 2 right here. And then for each element in the sorted array, which is just 3, SE here is going to be 3. If 2 is less than 3, then in the sorted array, which is currently 3, we're going to push 3. Okay. So now the sorted array is 3, 3. And we're not going to do this. So now it's going to continue. So now it's going to continue sorted array. And it's going to be 3, 3. Yeah, that makes sense. And then the output is 3, 3. Aha. Because the sorted array, I need to loop through it every time it increases in length as well. So it should go back to the sorted array here, 3, 3, and just do it again. Oh, wow. Okay. How do I do that? Because then the next element, or we're still going to keep the, we should still have the NTI up here, which is going to be 2, and then we're going to compare it to 3, 3. Okay, I understand what the issue is. It's like you have to restart the loop. Three, 3. But why doesn't it go back up here then? 3, 3. And then, because there's still another element in the unsorted array, which is 2, which is 1. And then 1 is going to be put here, so we've already lost the 2, which we're supposed to put in. So that's an issue. We've already lost the 2. It's kind of like we need to restart the loop, but how can we do that? No, that's not right. Because the array length here is just 1. Still 3, 3. I'm going to look up a solution in JavaScript and see what the difference is. Because I kind of know what's wrong, but I don't know how to fix it. It's going to be a while. Sure. While j greater than -1 and current, which is the NTI, is less than input array j input array. Like this. Is that different to what I'm doing, pushing somehow? I'm at the point where I'm just trying things. It's not good. Oh, equal. I see. So that's the same thing. Same thing. So if I change this to a while, no, can't be right. J minus minus. Oh, okay. So we're using j as the index. I is the so let j. I'm just gonna copy his thing. Let j equal I minus 1. This is the length. I equal 1. N is the length of the input array. Why is he not doing a minus 1 here? Because he's not using I to index. Current equal. He is. Current. I'm gonna call it NTI. Input array. I equal 1. Oh, the iteration starts at the second element. The iteration starts at the second element. Okay, so that's why it's 1. And then it's doing a while loop. While j greater than or equal -1. So it's on a loop forever. And current. I don't really get this solution. You're just manipulating the input array right away. So I'm guessing this should just work. 2, 3, 1. 2, 3. Oh, sorry. Wait, hold on. I must have an issue with my code. I'm using the unsorted array for. Yeah, it should be input array. What? Yeah, I'm just gonna copy paste. I have it misspelled. Oh. Yeah, there's definitely something wrong with my code. What is it? For I equal 1, I less than n, I plus plus, current equal input array, j equal I minus 1, while j greater than -1 and nti. I don't know why I have 2 returns. Yeah. Makes sense. Okay, so I'm trying to understand it fully because I mostly understand it. So you get I equal 1, you start at the second index. So you're ignoring the first element. I less than input array.length. Sure, that makes sense. And then I plus plus. And then NTI, number 2 insert equals input array I. Yeah, we're storing it in the variable, the current element we're on. And j equal I minus 1. While j greater than or equal -1. While number 2 insert is less than, yeah, while number 2 insert is less than input array j, so the number which is to the left of I, because I is 1 less indexed than j, the number to the left of the number 2 insert, if it is greater than or equal, if it is less than it, if number 2 insert is less than it, then we're just going to add j again to the end of the array, and then j minus minus, but it's a while loop. It's a while loop. And he's stopping at j greater than or equal -1 so that he makes sure he goes through the whole array. And then he's doing j minus minus. Okay. So that's going through the whole array. But then input array j plus 1 equals NTI. Oh, because this while loop is within a for loop. Okay. So then this line is what makes sure that he actually does insert the NTI, and then it goes through the rest of the loop and does the same thing. Okay, I get that. Yeah, that makes sense. Oh, that makes sense actually. Okay, I want to see if I can do it from scratch, on my own. Const insertion sort equal input array number array. And I'm gonna just make it as clear as possible like he did. Let n equal input array dot length. Then you have a for loop and a while loop. For let I equal 1, because we're starting from the second element, because the first element is already ordered. I less than n, I plus plus. And then you get j, let j equal I minus 1. This should be an arrow function. And that is a while loop within the for loop. While, then you got to make sure it stops. So j greater than or equal -1. And then the number to insert. Okay, we got to get the number to insert. So let current equal, and then input array I. And then current is less than input array j, right? Input array j plus 1 equal current j minus minus. minus minus. And input array once we reach the appropriate position to insert. Kind of losing it. I'm losing it. I'm losing track of it in my mind. J yeah, equal. Oh, this should not be current, I think. This should be iterate J plus 1 equal current. Is that right? Return array. Okay, here we go. It worked. It worked. So let me just try another array. I have some negative numbers. Negative 17, negative 5, negative 2, 1, 2, 3, 12. Okay. So that's insertion sort. How long did it take? About 45 minutes, but most of which I was just trying to do it on my own without looking at a solution. That makes sense though. I got to the point where I knew what I was doing wrong, but I didn't really know how to fix it. And then it took me about 5 minutes to do right now. So that's fine, that's good. So what's the complexity of this? The big O. What's the big O notation? Insertion, sort, complexity. It's O of n. Okay. The best case, no, I need the worst case. Yeah, n squared. It wouldn't make sense for it to be just n. All right, because you're kind of, it's a loop within a loop, so it would make sense for it to be n squared. Okay. Well, I'm going to take a short break. Then I'm going to go to the next algorithm, which is going to be selection sort, right? Yeah, I'm going to do selection sort next. It's kind of a bit harder to understand, maybe. So I'll try doing it though. So const selection sort equal. It's just going to be input array. It's going to be an array of numbers, and then it's just going to be a for loop for let n equal 0. 1 I plus plus let me just name it imin equal I, so this is an index, so we're keeping track of the minimum index for let j equal I plus 1 I plus 1 I plus plus It's kind of like if input array yeah, okay. So if input array j less than the input array I min we need to swap them, right? So I'm just going to create a temporary value, input array j, and then input array j equal input array I min, and then input array I min equal temp. Return input array. So let's see. Hopefully I did it right first try. 2, 3, 1. Whoa. Oh, it's definitely something wrong. J equal I plus 1. J less than or equal. It should be J. Or less than. Input length minus 1. And the J plus plus. Whoops. Okay. There you go. Selection sort. First try. Except for this issue, this minor mistake here. But yeah, this one was easier. There you go, man. I'll just try and randomize this order a bit. Negative 17, negative 5, negative 2, 2, 3, 12, 1. No, there's something wrong. If input array j less than. Really? There's something wrong? Why is the 1 at the end? Oh no. Oh no. Okay. I'm gonna look at the pseudocode here. Oh, this should be I plus plus. No, for I. Oh, J is the first one. I kind of swapped them. I less than N. So I have an extra -1 here. Why? This work? This does work. Length -1. Here it's n-1, here it's n. Why would it be n here? Wait, I did something different. I don't have this. I min not equal j. Kind of confused a bit. I think I did something wrong. I'm gonna make these j's. It's like I did a different solution, but it still works. So let me just make sure it works completely. Add some numbers. No, it doesn't work. It worked that time. This one does work. I'm so confused though. I just tried swapping the j's and the i's and it stopped working. J, j, j. I mean equal j. I equal j plus 1. Oh yeah, of course it's gonna stop working because these need to be swapped as well. Yeah, so this should work. Yep. I was swapping the i's and j's, but I didn't swap them down there. So this works. This works for sure. 1, 2, 3, 12. I mean, it works. So try and understand what I did differently and why it still works. I mean, I understand why it works. It makes sense to me. But I'm wondering, you know, what if I give it an array of length 1? Will that work? Or will it bug out? Okay. 2. Yep, I got an error. No, I didn't. It's just the compiler bugging out. So this works, this solution works, but I want to compare them. If A is less than, if the element at index I is less than the element at index minimum, the minimum element, then we change the the index of the minimum element into I, which makes sense. And if the index of the minimum element is not J at the end of the for loop, yeah, so I am doing it differently. We're supposed to do I min equal I, and then at the end, outside of this for loop, we're supposed to, if I min not equal j, then we swap. So this should still work. Yep. It's not working. Oh yeah, I'm supposed to, yeah, okay. My bad. Temp equal input array of j, input array of j, input array of min. This should work. -4, -2, 1, 2, 3, 4, 6. So that looks like it's working. Let's try changing it so it should be 1, 2, 4, 6. There you go, 1, 2, 4, 6. Okay, so that's, I did it the same way as the pseudocode here. So that's selection sort complete. All right. So next, let's look at quicksort. Oh, I want to check the big O notation. Selection sort complexity. Should be n squared, right? Yeah. N squared. And this is just n. Insertion sort is just n. No, this is the best case. I've already looked this up. It's n squared as well. Okay. Okay. What? This is very confusing. Okay. Oh, okay. Quicksort A is array, low is int. Okay. Whoa, dude. It's kind of frying my brain right now. Okay, I'm gonna let it simmer. I'm gonna come back to this later. Quicksort. Because I don't know if it's important to like just get good at every single one of these algorithms. But what's the time complexity for this? It has to be high. What? Oh no, worst cases n squared, yeah. Keeps telling me like average cases. But we only care about the worst case, right? Hmm. Hmm. Okay. So that's interesting. I want to take a look at heap sort as well. Heap sort and formants. So we just keep calling heapify and then swapping. Doesn't that seem counterintuitive? I'm guessing these sorting algorithms, you know, it doesn't mean that they're all useful most of the time. n log n only. Two n log 2n. Now these past two have kind of confused me. Interesting, man. Interesting. I'm gonna pause for a bit. Okay, so I've been watching. I rewatched this quicksort video, and it's still pretty confusing. But honestly, the most confusing part is the code here. So quicksort, and it's a recursive function, and then partition is another function that's defined on its own. So I'm gonna try to do it on my own, because I think I understand how to do it in my mind. But what I don't understand is after we pick the first pivot and we're done with that cycle, how do we know what the next pivot is going to be? You know, how do I define that? How do I get it to do it again and then just pick a new pivot? Do I just divide the array into multiple arrays, one array to the left side of the pivot and one array to the right side, and then just keep doing that every time, or what? Because that's what he did here. He took this array on its own. He took this part by itself after he's done with the 3. He took this part by itself and did it to that. But programmatically, how am I meant to do that? Like, how do you go from this to this to like have it all being sorted? That's the part I'm struggling to imagine right now. But it seems everyone else is also confused by it. So I'm looking at the pseudocode. Pivot equal a low. Yeah, we're telling it what the low is. We're telling it what the low is. Low is int. High is int. Oh, so no, I don't really. Is this us defining a subarray? So low is the beginning of the subarray and high is the end of the subarray, or what? Pivot equal a low at index low. Left wall equal low. Left wall. For I equal low plus 1 to high, if a at index I less than pivot, then swap a at index I and a at index of the left wall. If a at index I less than pivot, which is a low, left wall equal left wall plus 1. I don't really understand this. A low high, it's the same. If low less than high, equal partition A low high. Partition is this one. This is all within the if. This is confusing, man. Oh. But I'm glad it's not just me. So this is gonna take me a while to really understand. I feel like I understand the explanation more than the code. Partition. I'm gonna look up a solution. Quick sort JavaScript. Let's take a look at this one. Can I see a solution for it? Okay, so let's look at JavaScript. Low, high. Low, high. Why are we telling it low and high? Should it be high? We're just, I'm guessing this is arbitrary. Why are we choosing high as the pivot? Index of, or maybe in this case, it's just using the element that is already at the very right of the array. Index of smaller elements. Index of smaller element and indicates the right position of the pivot found so far. The index of the smaller elements. Oh, we're telling it what the smaller element and what the higher element is? Traverse array, low, high, and move all smaller elements to the left side. Elements from below. All smaller elements to the left side. Elements from low to I are smaller for every iteration. J equal low, J less than or equal high, minus 1, J plus plus. I still don't understand it. What? Oh man. Quick sort. I want to figure out the time complexity. Okay. I don't feel ready to write it as code. Well, this is the hardest one so far, I think. Same with the heap sort. I'm gonna watch another video on it. Oh, that's what it was doing in that JavaScript solution. Okay. Okay. So we'll take the 1 as the pivot, new pivot. Okay. Okay. Then we take 8 as the new pivot. Do I need to move those? So we need to swap them. Oh my god. Okay. This video is better than the first one. Because in this video, was it this one? In this video, he didn't make it clear how we're selecting the new pivots. That we can just take conventionally, we can just take the rightmost. He did it here, but it didn't really make it clear how we're doing that. No, he didn't actually do it here. This was the pivot in the second case. So that's what I was asking about. So you just take the last element of the new subarray and then do it again. You're comparing it to all the ones before it. And if the ones before it are larger than it, then you need to move everything, move it over, and then move that one to the beginning, or move that one to the left towards the beginning of the array. That's better. That's easier. That's more understandable. Yeah, that's what I was thinking. Okay, it's making more sense. Okay, so I found 2 really good videos. This video is super nice at explaining how quicksort works, and it's purely just an animation, and it just shows you with audios, with sound and visuals how it works, right? This helped me a lot, and I still haven't tried to code it myself, and I've also watched most of this video here to get a feeling for how coding interviews are like. This is, again, NeetCode, great channel. So I'm gonna watch this video again, and then I'm gonna try code it. Code the quicksort algorithm. So I'm gonna try it the way where the last index is the pivot. You compare 3 and 4, and then 3 is less than 4. So you move the orange one to that as well. It's also less than 4. 5 is going to be more than 4. So what's going to happen is you flip those two. No, not yet. 4 is less. Okay, I don't really understand this part that well yet. So it's less, so you move the orange one as well. It's more. So what do? You keep the orange part where it is. And then this one is also less. Green is less. Orange plus 1. And then if green is greater than orange, Swap green and orange. Hold on. I'm checking from the left side. You got 2 pointers, the green one and the orange one. 5 is greater than the pivot. Pass. Do nothing. Less than the pivots. Add the index. And then if green is greater than orange, but it's not in this case, so why did he swap? Or is he talking the index is greater for green than it is for orange? But if they're on the same index, then you pass. Okay. This flowchart down here is very helpful. Oh, he did swap here. Oh wait, no, this is the same one. But they're on the same one, so there's no swapping yet. Ah, I see. That's why he didn't swap here, because after you add 1 to the orange index, then they're on the same one, so there's no swapping. Well, this one is greater, so you're just gonna pass. This one is less, and even after you add 1 to the orange index, the green index is still greater, so then you swap green and orange. Swap the elements. And then keep going, doing the same thing. Swap those two. This is greater, so just pass. This is greater, so just pass. The rest are all greater, so you're just gonna do nothing. And then the one you're gonna swap the pointer with the orange one at the end. Oh, you're gonna add 1 and then swap. But you're not swapping the pointer, you're just swapping the one. I shouldn't think of it in terms of swapping the pointer. I should think of it in terms of, oh, the green index is now at the end, which is also the pointer. And so that's why I'm gonna swap, because there's a less than or equal here. So that's crucial. Okay. Now, how do you partition? Do I just use the index of, I just use the index, which the orange stopped at, right? Then I call quicksort for each of those. So that's why it's recursive. This part is still kind of hard for me to simulate, like to how I'm gonna do it with code. But I'm gonna try doing this part so far. And I'm gonna have it on my other monitor. And open VS Code. Okay. Const quick sort equal. So what does it take though? Does it only take an array? Probably not, it takes more, right? Okay, let me go to the beginning. This one's pretty hard. Current index, pivot value. Swap marker. Just a for loop through an array. So so I watched in that other video, it said a common method to get the first pivot, the first number to start pivoting around, is to get the median get the first value, get the value in the middle, and get the last value in the array, and get the median of these three. And now I'm assuming that's fine to do because each of those operations, getting a value from the beginning, middle, and end, it's going to be O of 1. So it doesn't matter if I'm adding O of 1, O of 1, O of 1. This is going to be O of 1 plus 1 plus 1, and that's a constant number. So I'm guessing that's why they can do that, because it doesn't really increase the complexity of the algorithm. So I'm guessing that's why they do that. So I can do that. And I can actually just do that, even though I don't need to. Just first lm equal input array 0, and then do that for the second in the middle. This should be last, and then this should be middle lm element, and input array math dot floor input array dot length over 2 minus 1 over 2. But am I going to have to sort these three? So if I sort these three, it's always going to be 3 elements no matter what. So that's also another constant. You know, it's adding another constant to the time complexity, or the big O notation complexity. So that's fine, I guess. Const median equal first lm middle last dot sort, and then just the second element. But then I'm going to have to move that element to the very end of the array anyway. So will that also, isn't that going to raise the time complexity? No, but I already know where that element is. So if I move it to the end, I can actually I can actually just maybe swap the positions of the middle elements. But here's the thing, I don't really know which one of these is going to be the... After sorting, I don't know, depending on the input array, which one of these is going to be the actual pivot, right? It could be any one of the three. So instead of using a sort here, I should be able to know for sure somehow. This cannot be the most efficient way, but what if I just do a switch case where, depending on which one is the median, then I would move that one to the end of the array. I mean, that would work, no? That wouldn't work, though. So first case would be first lm less than and lm greater than middle lm and I'm going to make a swap function just to simplify this code. Const swap function, the swap elements equal a, which is array of numbers, b, and c. Number. Let temp equal c. These are going to be indices. Let temp equal a at index 1. A at index 1 equal index 2, b a index 2 equal temp. Return a. So this can help me swap elements in an array. I need to give the array the indices I want to swap. So let me just test it out. One, 2, 3, and then that's just 2 and 0. I'll just comment this and try running. Three, 2, 1. Okay, that makes sense. If I want to swap 1 and 2, it'd be 2 and 3. All right, so this works. So let's use it in our quick sort. So first case is the first lm is the middle one. First lm less than last lm and first lm greater than middle lm. Or first lm greater than last lm and first lm less than middle lm. Put these in parentheses. This is going to be a messy solution, but I do not care. Then input array equal input array dot swap swap input array, swap elements input array, and then 0, which is the index of the first lm, and then I want to swap 0 with the last element. Input array dot length minus 1. And then in case that's not true, I want to check if the middle lm is the actual median. And I'm just going to copy the code. In this case, middle lm, first lm, fits in between that way, middle lm, first lm. First lm is less than last lm, and first lm is greater than middle lm, so that means it's in the middle, and this also means that it's in the middle. but they're just going to be, the other two are going to be swapped. Input array, I'm going to swap. And in this case, middle LM is going to be in the middle, both ways possible. And then input array equal swap elements. In this case, we want to swap the middle with the last. So the middle is going to be this. Input array and then the middle is going to be this, and the last is going to be input array dot length minus 1. And then if it's the last element, then we don't need to worry about that because it's already the last element if it's the median. So let's try it out right away. I'm just gonna return input array. Just do nothing. If both of these are not true, then just do nothing. So console.log, and this isn't the full quicksort function yet, but let's just see if the pivot selection works just fine. So let's give it an array of 1, 3, 5, 7, 9. So the median here would be 5. But if I make the 5 at the beginning and the 1 in the middle, so the 1 should be here and the 9 should be there. So the 1 and 9 should swap. Five, 1, and 9. The median is 5. So 5 and 9 swap places. Yeah. That makes sense. The median is 5, so 5 and 9. 5 went to the very right. Now if I put 5 in the middle, it should also give me the same result. 5 should be at the very right. But 9 swapped with 5 in the middle now. So that's fine. So if, for example, median now, I want the median to be, 4. So then this should give me the same array. 1, 3, 5, 7, 4, 1, 3, 5, 7, 4. Okay, so that's good. We're selecting the pivot well, the way the video said. Okay. So now we have the new input array. Now we have the input array with the pivot moved to the very right. So it's going to loop through each element. Okay, so for let I equal 0, I less than input array dot length minus 1, I plus plus, and it's going to be if const last, I don't want to use the same variable name. So I'm going to name these elements equal input array dot length minus 1. So now we have the pivot. Let's just name it the pivot actually. And if the element at the index that we're currently in, if I understand correctly, is greater than the pivot, then we pass. If it's less than or equal, we should do a let here. Let swap equal I. If input array at I is less than or equal pivot, which is the last element, then we add swap, we do swap plus plus, we add one to the swap variable. And then if I is greater than swap, we do something. And then if I equal swap, we do nothing. We don't do anything. We pass. If I greater than swap, then we switch the green elements and the orange elements. So swap the green element and the orange element. So we input array equal swap elements, input array I swap. Otherwise we do nothing. But how can we tell? So when it's going to be done, the orange is going to be at the position of the element who we know is in the right position, and that's when we should split the array, right? So we know we should split the array at the position of the swap, which is the orange circle from the video. So how do we split the array in two, and then we have to call quicksort for those resulting arrays? Sure. So we have to split the array. So we can just do that using slice, right? So after the for loop, we call quicksort. But how do we know if we're done? 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 So do we just we're definitely not going to call quicksort in the actual loop here, right? Swap commas. Okay, this can't be the right way to do it, I don't think, but I'm just gonna check if I'm not sure how to do it. How do I know how to stop? How do I know how to stop? How do I know how to stop? I'm gonna go back to that other video. This one. Because I think the pseudocode might help me.
Today, I think you understand the concept, so we'll let recursion handle the rest. Possible to even.
Yeah, so how do you stop?
Quicksort
I
has
don't
the
know.
worst case time complexity.
This pseudocode is
And as you can see, it's not too far off.
hard to understand.
Here's the
I don't know what he means by low and high. If low less than high. What do you mean? No, I do not understand this pseudocode. Okay. How do I know that it's sorted? So there has to be a way for me to know if the array is sorted if we're done. But I'm just gonna do it. I just want to make sure my code works. Obviously, this would not be a good way to do this, but I'm just gonna, if input array dot sort equal input array. I just want to make sure my code works. Then you do quick sort. Then the swap at the end of the for loop is going to be at the element that we know is at the right spot. I'm just going to flip it into two. It's going to split it into two new arrays. So quick sort and then input array dot slice from 0 until is this This is exclusive at, okay, swap. But I don't have access to swap outside the for loop. But I can change that. But then you do quicksort for the from swap onwards, which I think should be like this. Yeah. Let swap. What do you mean? Oh yeah. So just initialize it at 0 maybe. What? Oh. Swap starts at 0, starts at 0 anyway. But it's gonna be reset every time. Wait, no. This is wrong, isn't it? Looping over the, yeah. This is wrong. Yeah. Because we don't want it to be set to the current index we're on every time. It should stay marking the element that we found, which is less than the pivot. So I'm going to try it now. And then if I just return the input array here, then these will also return the input array. And during the recursion, it should fix up my array and make it sorted, right? Understanding this right? So 13574 should just swap, it should just be 13457. So let's try. Worked. This is an old console log, right? Don't need this anymore. It worked. Let's try it with more numbers. 5, 2, 7, -2, 3, 4, -1, 6, -10. Something's wrong. It only got one of them wrong. So -1, -10 should be -10, -1. -2, 2, 4, 5, 6, 7. It only got one of them wrong. That's interesting. I wonder why. There has to be an issue with my code. -1, -10. That's interesting. Because this should not include the swap. So this is fine. This is exclusive. This is inclusive, rather. This is exclusive. So what's the issue? It's like it's almost working. I wonder what the problem is. I have such a minor error in the output. And I'm gonna console.log input array. Whoa. Input array dot sort. Maybe the issue's here. So they're not equal. Oh, it is. Is it being called multiple times? Why am I not seeing multiple inputs? Because I'm calling quicksort here as well as here. Am I losing my mind? Whoa, here's the issue. This should be out here. Right? I'm gonna kill this terminal. I feel like something's wrong. How come it's only calling it once? So input array I is less than or equal to the pivot is I greater than swap, which means it's Adam. Which means it's at a greater index, which is what we saw here. This is I. This is swap. And swap. Oh. So I'm not sure what the issue with my code is. So I'm just gonna try giving it to ChatGPT and then ask it what the issue might be and tell it that it's supposed to be a quicksort algorithm. So let's do that. Let's do that. So this is what ChatGPT says. I'm not capturing the recursive results properly, but not capturing or using the return sorted subarrays. Need to store the results and combine them in a new array. Okay, I can see that making sense, yeah. And you increment swap before checking if algorithm swap. Oh, yeah. Of course. I knew there was going to be something wrong here. Oh, I have an issue there as well. Okay. So yeah. And then I knew there was going to be an issue here. So I don't need this at all. So the first one, yeah, right here. Yeah, that check is always going to return true. I don't really understand this part. Because I was just following the flowchart in the video. So I'm going to leave it as it is and just try it. Whoa. It's a TypeScript error. What? Oh, it's just an any error? Whoa. That's interesting. Maximum call depth exceeded. So I'm gonna do the fix here then, and let's just see if it works. Just doing the logic differently. Wait, hold on. Shouldn't this part be outside? Like this. No. What's the issue here? What? What? I'm just gonna remove this part because it's not necessary anyway. This whole part. Next one, call stack. Maximum con. I feel like I'm just not able to think anymore. So I do understand what he's doing here, or what ChatGPT is doing here. I'm just gonna copy this and try, see if it works. Instead of, yeah, it's just kind of condensing the logic. Or you're just pushing, you're making the arrays up here and you're just pushing into them right away. And then you're just returning, even here, just returning the result of the quicksort function. So let's see if it works. -10 to -1, 2, 4, 5, 6, 7. Yeah, it works. So let me just understand the for loop, because that's the only difficult part right now. This like has made it a lot simpler for me. Pivot is just the last element right away. That's the pivot. So it just loops through everyone, and then instead of just storing things in variables unnecessarily, if it's less than the pivot, then it just pushes it right away into the left array. Else, it pushes it into the right array. If it's less than the pivot, it pushes it into the left array, and if it's not, then it just pushes it into the right array. So why wouldn't I just do that? Like, this just makes it a lot simpler than the video did. Pivot is the last element, and then you just measure everything against that, and then you just call it recursively, and it just takes care of everything. Yeah, this has definitely simplified it for me. I can do it like just based off that understanding. Cool. const pivot equal array, and this should be an arrow function, array dot length -1, and then const left, same with right, and then just for let I equals 0, I less than array dot length -1, I plus plus. If I less than pivot left dot push I, else right dot push array I, also up here array I. And at the beginning I should just check if array dot length less than or equal 1, return the array. And then after this, return quicksort left pivot quicksort right. Then you just what? Oh, what? What do you mean? So we just do this, I guess. Sure. It's freaking TypeScript error. -10, -2, -1, 2, 4, 5, 6, 7. Yeah, after I saw the solution, it's so much easier to understand. Because it's just gonna, the recursive part is easier to understand, and this makes it a lot simpler. Where you just read the array length. And if it's 1 or less, then it's automatically gonna return the array. Save time as well. Okay, that's quicksort done. I did it from memory, or from just based off understanding. So sure, that's quicksort complete. The last one I want to do today is heap sorts, which was also pretty hard to understand. I think this is the channel that I was just on. No, Curious Walk. Nope, they don't have a video on it. Sure.
Let's dive into how the heap sort algorithm works. But before we begin, it's crucial that you are comfortable with the concept of heaps. If you are not familiar with heaps, I highly recommend checking out my animated video on heaps first. The link is in the description below. It will make everything we discuss here much easier to grasp. If you already understand how heaps work, you are all set. Let's get started. Here is the complete binary tree representation of the array. Now, the very first step in heap sort is to build a max heap from this array. This step reorganizes the elements to satisfy the heap property and runs in linear time. Once again, if this concept feels unfamiliar, be
Runs in linear
sure
time.
to check out the video on heaps first. Once the max heap is built, we move on the next step. Swap the root element, which is the largest value in the heap, with the last element of the heap. And after swapping, the largest element is now in its correct sorted position, so we can ignore it for the rest of the sorting process. However, this swap breaks the heap structure because the root is now replaced with smaller element. To fix this, we perform a heapify down operation to restore the heap property and maintain the max heap. And just to be clear, everything we are doing here is happening within the array itself. The binary tree we have been looking at is purely a visual aid to help our human minds better understand what's going on behind the scenes. This process of swapping the root with the last element and then performing heapify down continues until all elements are sorted. I will pause the voice over here and let the algorithm complete.
Okay, so once we remove an element, I think if I just look at the bottom part, it's easier to understand.
This, we perform a heap, which is the largest value in the heap, with the last element of the heap. And after swapping, the largest element is now in its correct sorted position, so we can ignore it for the rest of the sorting process. However, this swap breaks the heap structure because the root is now replaced with smaller element. To fix this, we perform a heapify down operation to restore the heap property and maintain.
Heapify down.
And just to be clear, everything we are doing here is happening within the array itself.
So the heapify down.
Element. To fix this, we perform a heapify down operation to restore
Put
the
it
heap
this
property
way,
and maintain the max heap.
that way.
And just to be clear, everything we are doing here is happening within the array itself. The binary tree we have been looking at is purely a visual aid to help our human minds better understand what's going on behind the scenes. This process of swapping the root with the last element and then performing heapify down continues.
Okay, I think I need to look up what heapify is. Heapify. Explains.
Next, let's try inserting an element. We could take the approach we used with BSTs. Start at the root, then move down the tree one level at a time and do comparisons until we find an open spot. However, if our element is bigger than most of the parent nodes, or even the root, we'll need to shuffle the tree around a lot. As such, we take a different approach to inserting here. We can stick the new element in the next open spot in the tree. Then we heapify. Heapify is the operation in which we reorder the tree based on the heap property. Since we care that our parent element is bigger than its child, we just need to keep comparing our new element with its parent and swapping them when the child is bigger. We can take a similar approach to an extract operation, where the root is removed from the tree. We stick the rightmost leaf in the root spot, then just compare it to its children, and swap where necessary. The runtime of insert and delete,
Okay.
a more general case of extract, ends up being O of log n in the worst case. Ultimately, the worst case would involve moving an element all the way up or down the tree, and would roughly be as many operations as the height of the tree.
You got it. Okay, let's watch some more heaps.
Today we're going to learn
videos.
about heaps. You often hear the word heap when discussing storage for garbage collection in languages such as Java. But this video is about the heap data structure that is used to manage information. Heaps are sometimes called binary heaps and are nearly complete binary trees. Here's an example of a heap. By a nearly complete binary tree, I mean that all levels are filled except the lowest, and the lowest level is filled up to a certain point starting from the left. Uses of heaps include heap sort and priority queues. And there are two kinds of heaps, max heaps and min heaps. On the left, we have a max heap. The condition for a max heap is that the value of the node I is less than or equal to the value of its parent. Max heaps are used for
That
heap
makes
sort.
sense.
Similarly, for the min heap, the value of the node I is greater than or equal to the value of its parent. Min heaps are great for priority queues. Because we said heaps are nearly complete binary trees, we know that the height of a heap is big O of log n, which you'll see in various operations that we'll learn later. I'd also like to show heaps represented as an array. Here's our max heap, and here it is as an array. The root of the tree is at index 1 of the array. To get a node's left child, you simply take the index times by 2.
Oh yeah, okay, that's useful.
And to get the node's right child, you take the index times by 2 and add 1.
Plus one. That makes sense too.
Finally,
That's
to retrieve a
useful
node's
to know.
parent is the floor of the node's index divided by 2.
Okay, sure.
We choose to put the root at index 1 instead of 0, as it keeps this arithmetic cleaner, and most computers can do these operations with fewer instructions. Let's take a look at 15, which is at index 3.
What did he just say? Puts the root at 1 instead of 0.
Let's take a look at 15, which is at index 3. The left child of 15 is equal to 2 times 3, which is the 6th index, and the node value of 12. The right child of 15 is 2 times 3 plus 1, which is the index of 7, or the node 13. Lastly, the parent of 15 is the floor of 3 divided by 2, which is the first index and the root of our tree, 21. You know I prefer brevity, so we'll end the video here, and in the next one, I'll show you how to create a heap from an unordered array. Thanks for watching.
I'm going to spend some more time learning about heaps and heapify before I try to write the heap sort algorithm. But let me take another look at the roadmap. So after heap sort, I'll be done with all of these. And then there's some data structures that I want to understand. So a queue is, I want to understand what a linked list is. A hash table, I think it's kind of like a dictionary in Python, or even like an object in JavaScript, but I'm gonna have to look into that as well. I know what a stack is, I know what a tree is, I know what a queue is. And then the heap is over here, and then there are multiple types of graphs. Oh yeah, and then there's binary trees and sure, okay. Tree traversal graphs, A-star algorithm. I remember this from college as well. Greedy algorithms, oh man. I think this is going to get more and more complicated. Well, this is day 1 still, so being done with the sorting algorithms and these searching algorithms. It's been a pretty good day, but I think with programming or topics like these, you just kind of have to take a break. Like you get to this point where your brain just does not work anymore, does not work as well. And you're just listening to the information, but it's not registering. So I'm going to stop here and we'll see what happens on day 2.